Okay, it is my pleasure to introduce. Let me just worry. Okay, that's Professor Chen, Daphne Chen. She is a professor in electrical engineering. She joined the department like 3 years ago, no? 2 years ago. So she's one of the really big persons in electronics at this university study. She's doing a fantastic job in developing new electronics. And I think today is going to talk about beyond CMOS, materials, emerging memory, and applications. And I really think we have a lot of collaboration here. And as you know, electrical engineers are the closest to physicists. Okay, go ahead, please.
Thank you, Miguel, so much for the great introduction. And my name is Daphne Chen, and I'm currently assistant professor at electrical engineering. And I'm working on.
If you can speak closer to the microphone.
Oh, sure. Yeah, my problem is to keep moving during the talk. Sorry. So, okay, so let me start again. So, as you know, I'm the professor at 6, and I'm also affiliate professor in MIRA. So, yeah, I'm kind of like very honored to join the MIRA group. And let me bring a little bit more introductions about myself. So I born and raised from Taiwan, and I got my bachelor and master degree in material science and electrical engineering. And then I went to UT Austin in Texas, which is very hot in summer, well, in winter as well. And then during the time, I went to IBM for my internship, and I stayed in Poughkeepsie, Upper State, New York for half a year, and working on SRAM design and fabrication. And then I come back to UT Austin to finish my PhD. And then after that, I joined Micron Technologies as an R&D pathfinding emerging memory engineer, working on memory. So basically from my college, well, long time ago, I started working on memory already, and I'm a lover of memory. So I hope I'm the person to share some memory story to you today. And thank you for coming, especially late afternoon on Thursday. Okay. All right. So some introduction about my group at electrical engineering at NAU. And our group and focus is focusing on new materials and new devices for emerging memory, new computing, and solve electronics. And due to the time limit, I will not be able to talk about solve electronics today. But if you are interested, you can check it. But for now, I'm working on semiconductors and memory technologies. And then what does that matter? It matters because there's a booming in semiconductor. That's number one. Number two is we have a bottleneck for computing. So we want to bring memory into computing. So if you heard about neuromorphic computing, synapse neural mimicking computing, that's all related to memory. So we're trying to realize the computer CPU working as a function as your brain. Okay, so that's basically the key takeaway. But traditionally, we do worry about the storage plus memory. So we are trying to working on emergent memory, and I will introduce a little bit about selectiveless RAM today, just a piece of my work. So I do have my QR code, and I do hiring right now. So if you are interested, contact me. And after my talk, well, you can think about that. Okay. So what does semiconductors matters? So we are in Arizona, and it is a big deal. So what I'm talking about is the CHIP Act and Science Act, which is officially signed in 2022. And there's bring a lot of investment because a lot of the history back to 30 years ago, we do have a lot of manufacturers locally in the United States, but because of cost and human force cost down problem, so all moving to Asia. But now we are worried about that we don't have a capability and manufacturers powers locally here. So that's the reason why you see a lot of people holding the wafers like me, what I'm doing right now, because we want to bring up back the manufacturing power to locally. So let me zoom in a little bit to Arizona. So we are here at the yellow highlight Flagstaff. and we are really not far from two important fabs. Number one is Intel, which already been in Phoenix for a long time. And the other one is newly built, which is TSMC, Taiwan Semiconductor Manufacturer Company. And if you drill down to Phoenix on your right-hand side, you're gonna see a lot of constructions. That's a site, that's a space sheet for TSMC. And they are doing 5 nanometer, and they are hiring a lot of people. And this is just highlight 2 fabs, but for supply and other related companies, they will bring a lot of working forces. So if you consider to join semiconductors, think about the locations, which is quite advantage because you are in Arizona. And besides of that, let me zoom out a little bit. For United States, we do have Silicon Valley, which is actually starting with the hardware silicon. So that's starting with the chip manufacturers, but now it's kind of transferred to the software applications a lot, but they are trying to transform a little bit to modulate it, to adapt to the Chip and Science Act. And Silicon Hill, Austin, Texas, you're gonna see the house price is rising a lot. When I was a student there, it's totally different. And then Silicon Forest, Oregon. So Intel headquarters is in Oregon. Okay, so it's Hillsboro, and rents a lot, but it has a beautiful mountain and Japanese garden. Okay, Silicon Desert, which is us, Arizona. And like I mentioned, Intel, TSMC, and then Silicon Alley. If you reading some news, there's a waking up on the East Coast, which is like IBM, Yorktown Heights, Poughkeepsie, Albany, all the way to Syracuse. And Micron Technology is building a new fab in Syracuse, which is costing 100 billion in clay. And then on the other side is Ohio. So Ohio State is the new home of Intel. So as you can see, there's a lot of fab is going on right now. And this brings the chip manufacturers more and more important. And there's a lot of jobs coming in. So if you're interested, do consider it. All right, let me go back to my talk today. So memory is one type of the microelectronics in semiconductor technology. And my research is focusing on memory. So this is today's outline. First of all, I will introduce the current challenging on CPU and memory. And then I will talk about why I'm working on selectiveless resistive random access memory, which is memory doesn't need the access device. And then I will zoom into the result and discussion, which is nonlinearity in bilayer state RN devices, and then self-selectivity optimization and physical model, and device-to-device variation and solution to that. And that's a downside for RN devices currently, but I gonna bring some solutions as an engineer by training. And then I will be very excited to talk about some ongoing projects I'm working here with all my colleagues, and which is including the helical-shaped hybrid electronics selector and memory, and reprogrammable one-time programmable memory, and radiation effect on memory. So some people research center are trying to bring the manufacturer to the International Space Station, ISS, and I'm focusing on how to deal with the hardest treatment on the memory. So this is today's outline, and I will conclude my talk. Okay, so number one, why memory is important. I think I have a brief introduction, but this is just trying to convince you. So in our daily life, there's a lot of memory chips, and as logic chips. And then network, transportation, automotive, high performance computing, supercomputer, space station, and mobile devices, healthcare, storage class. And if you do have your credit card, and if there has a small amount of storage for with your microprocessor. So there's everywhere. So memory is very important nowadays due to the human, it's a big important component for our human life. So let me know about, more about the memory hierarchies right here. So this is the memory relationship between the CPU and the storage. So the bottom of your period, which is capacity, large capacity, and then the top of pyramid will be closer to your CPU. So current architecture is transform data from CPU to storage and from storage to CPU. So there's a lot of transportations. And this is how the computer works. And so that's a lot of different kind of categories for memory, which is needed in different kind of location for in your CPU. So for example, SRAM has the highest speed, but smallest capacity. If you check your laptop, you're gonna find the exactly number. And then NAND flash has the largest capacity, but it works really slow. So this is the pyramid for the memory. And as the big data coming in, a lot of processing computer performance needed, required. We are thinking about, can we find certain immersion memory to bridging the gap, and which can do computing and also can do storage. So we can break out that transportation, a lot of power consumptions and traffic between your CPU and memory. So that's a key highlight of this pyramid. And we're going to talk about the volatile and non-volatile scale memory later on in the talk. But I just want to show you, as you can see, how much difference between the latency from the top of your pyramid to bottom of the pyramid, and also capacities is a huge difference. So there's a gap between computing and storage. And this is what we, as a memory person, we want to bridging the gap. Okay. Now let's narrow down a little bit. Like I mentioned, volatile memory and non-volatile memory, the most easy one to think about that is without the power supplied, the information will lost. That will be called volatile memory. And non-volatile memory means that even without the power supply, your information will stay in that memory for a long time. So it has a very good retention. And then the volatile memory, including SRAM, DRAM, and then non-volatile memory, including the compact disk, HDD, and flash and immersion memory. And if every one of you has a thumb drive, then that's flash memory. So basically, yeah, mine is in my bag, but the flash drive is one of the very good example that you're using. I hope I'm not too old to using that. I know everything is kind of cloud right now, but I still need it. So, so the thumb drive is the flash memory, and there is a certain bottleneck currently for the flash memory. So flash memory is based on transistor. So you have a source draining gate, and there's a floating gate. You store your electrons or holes in your floating gate, which writing 1. And then if you erase that hole or electrons, then it's writing 0. So for memory, it's 1, 0, 1, 0 operation, right, in the whole computing architecture. So, but as the scaling trend for the transistor, then there's becomes smaller and smaller in this flowing gate, then there's a bad retention happened because it's too small area you can store your electron or holes. So that will causing the retention error, and you will need more ECC to correct that in your array, and it will slow the speed and causing a lot of errors. So that's the reason why we're bringing in the immersion memory coming out. There's 4 kinds. So number 1, magnetic random access memory. Number 2, ferroelectric random access memory. Number 3, phase change memory. Number 4 is resistive random access memory. And my research is focusing on this, the resistive random access memory. And there's still a lot of people are thinking about which one is the better candidate for what just talking about the bottleneck. Okay, so a little bit applications for non-volatile memory. So most of the 4 immersion memory, those are non-volatile memory. And there is a lot of applications can based on those 4. Number 1, storage, of course, that's like replacing the flash memory. And 3D flash memory right now in industry is still working fine, but as the scaling happen, then we need to move to immersion memory. And then the second one will be the new computing configuration. This is what I talk about. So you have your process unit, you have memory, and there's a bus transport your data back and forth from your CPU to memory. And there's a lot of traffic, power consumption right here. So this architecture, we call it von Neumann architecture. This is a very classic computing architectures currently. We are still using it, but we want to break this memory wall. And a lot of researchers are working on how to bring the neuron-like or synaptic-like behaviors in your memory. So as you can see, if you're using this non-volatile memory as a component, then you can operate it like the more analogically like your brain, what is functional. So this is one. The other one is logic gate. So you can using the emergent memory component because it has a multi-stage. So you can using that to perform a different logic gate. And those are just two kinds of new computing. There's a lot going on right now. Okay, so multiplexing computing or so on and so forth. Those are based on the emergent memory component. Okay, and then the third one will be hardware security. So because RM or a lot of emergent memory has a good randomness, and we can take advantage of that randomness as our storage component for the hardware security. So no one can break that. And this is more reliable for storage your personal information. So those are three component applications that currently based on the non-volatile memory. And you might be thinking about which one is the best. And this is a small little table summarized by the CTO at Micron Technology, Scott DeBoer, in 2018 in VLSI. And they compared different typical memory technology, SRAM, DRAM, and NAND, and all four kind of emergent memories. So based on the volatility, cell, scalability, write and read energy and retention or cost, then you can find there has a trade-off, always like back and forth, but RM as itself, why I choose that as a research topic is because it's number one, it has the non-volatility. Number two, it is simple structure, two terminal, high scalability, high speed, low cost. I'm going to talk about how low cost it can be. And then it is low power consumption. So this is how RM as one of the candidates that we are trying to studying right now in the emergent memory. Okay, right. And I want to narrow down a little bit about my talk. So this is RM. And what is RM? So I want to quote it, Professor Leon Cho at UC Berkeley in 1971. If it's pitched, then it's a memristor, and memristor is ubiquitous. So this is the first time that one of missing component in the RLC circuit. So you might know about RLC, but there's the other missing component which can do storage and also computing, and that is memristor. And he mentioned about if that's pinched in your IV curve, then that's you can write 0 and 1, 0 and 1. Okay. And how about the microstructure of RM? RM actually is very simple. It's metal insulator, metal, and if you break down, you create the filament. And if you rupture the filament, then there will be high resistance state. So back and forth, 1 and 0, 1 and 0, you can write all the storage information in your component. And your IV curve is similar to the what I just described. So basically changing the resistance. So why there's talking about resistive, right? Because it's changing the resistance. Okay, and the beauty of that is two terminal devices is easily to integrate into the crossbar structure. So we are looking for ultra high density memory to adapt our computing need, right? So this is crossbar, that memory person, bring it out. We want to bring this crossbar for the high density memory, but there's a big downside of this, okay? There is sneak path current. So think about that. It's perpendicular to each other. And if you try to read this selected memory cell, there's inevitable current will passing through from your neighboring cell. And because you apply VREAD and 0 here. So basically VREAD and grounded here. So there's a lot of sneak paths as your array going up, the array size going up, the sneak paths will be more and more severe. So this leakage path will causing read and write error. And this is the problem that I'm trying to solve. And the worst case is that when your neighbor is under highly conductive state and yourself is at the high resistance state, so it will flip. It will be easily to flip your state. But basically, leakage will creating the conductive filament unwanted. Okay, so this sneak pass current is the bottleneck that if we want to achieve that high density storage class memory. So current solution, what does the TSMC and also Micron technology they are doing is using 1S1R. So if you have leakage, then I give you some transistor right next to it to clamp it. So this is we call 1T1R or 1S1R architecture. So they try to integrate the transistor right next to memory, each one by one. So this is kind of a lot of different kind of selectors, transistors, access devices that currently people are working on. So traditional TFT CMOS style and most insulator transition, IMT material, phase change material. And this is also done by one of my previous work, but this is based on the thermal driven. So you can change the conductance, and this is Intel and Micron's 3D crosspoint project, and which they get terminated because the high cost like 1 year ago, but it's still a big going through back 2 years ago when we realized the emergent memory in the industry really. And then the band engineer. So if you are familiar with band structures, then you can using the Schottky barrier as your switching behavior. Like you can clamp some current if you wanted to turn it on and using the barrier. So this is highly back-end offline compatible. And this is what industry people are looking for as well. But there's a problem for 1S1R. So think about this. Transistors is usually much larger than memory. Memory is 4F squared. Transistor can be 60 to 30F squared. So if your array has a lot of transistor and there's a lot of footprint for transistor, then that will cost a lot, and that will occupy too many footprints in your memory chips. So what I'm thinking about is, if I can get rid of this transistor and make the memory itself has a self-rectifying behavior, then that will be great. So in terms of the footprint reduce and in terms of the cost reduce, and that will be something that which has a breakthrough in the industry for the project. So my key takeaway is selectless RM means that I want to get rid of this transistor, and I'm going to talk about how. So this is the fabrication, and I think I can go through really quickly on this one because I'm now speaking to material scientists. So this is starting with a silicon wafer, and then you have bottom electrode, you have some photoresist, you have isolation, create some via, and then you deposit your active layer, MIM structure, right? Remember the memory devices I just talked about. So your RM devices are here in your small little via. And then I included bilayer structures, so which is hafnium oxide, silicon oxide, hafnium oxide graphite, and bilayer structures giving us some magic in the self-rectifying behavior. And here is what I want to show you. So traditionally, RM devices look like the flat curve. So if you switch high resistance state to low resistance state and low resistance state to high resistance state, this is a butterfly curve. You can store 0 and 1. And as I mentioned, there's a lot of leakage for the traditional RM devices. So the red curve is a bilayer statement structures. So you see there's a quite difference IV curve for the traditional standard RM devices and the bilayer structure, right? How does that work to suppress the sneak pass current? So if you have your unselected cell, which is your neighboring cell as a green one, stand by here in the 1/3 V read, and you still have a high current for your V read, then this steep slope will giving you the self-rectifying behavior because you reduce the current from this point to this point. So your standby current for your neighboring cell is actually reduced. So this is self-rectifying, easy, right? It's just one line for rectifying behavior with the slope in your IV curve. And this is just a median of a lot of device tested and also cycle to cycle variation. So this is just not one-time measurement. Okay, so this is what bilayer staking structures have been shown here. And as you can see, we want the slope as steep as possible. So you have a selected cell as a high current read and unselected cell as a low current read. Then next question is, how large can this self-rectifying behavior of RN reached for the current storage class memory? And I do some simulation. So this is the black one is the traditional single layer RM devices, which is 2 by 2. And this one we can reach to 120 by 120. So it's still improving it with a different combinations of bilayer staking structure. So this is just a key takeaway. And compare of the power, PCM, 1T1R, NAND flash. So as you can see, the power is compatible. And to be honest, MRAM is still the lowest power right now. So that's the reason why Samsung and Intel, they are focusing, Intel and Micron, they are focusing on this development right now. So, but key takeaway is that it's already being improved from 1T1R and phase change. So this is what selectorless RN devices has some beauty in that. And we take the time, should be 15 minutes. I'm a little bit worried about that. Okay, so let me do a better time control. Okay, so the optimization for it should be 1 minute per slide. I'm sorry. Okay, so this is how we can optimize that slip slope. So as you can see, there is an operations window for your set compliance current, and there is definitely a sweet spot for that operation. So we do need to do some control for that. And this is a model for how do you control the filament. But due to the time limits, I might leave that to the paper if you are interested. But key takeaway is that we have a high K and low K staking. And after a lot of modeling testing, then we found out that if your switching gap is located in low K layer, then that will be giving you the highest dip slope. So that's the reason why we are looking for silicon oxide. And we do some temperature testing to detect the gap, the switching gap, which is quite small. It's like a few nanometer, 1 to 2 nanometer. And this is creating by atom. So as you can see, the filament can be relaxation with the temperature. So I do tested 3 kind of different structures with the time. And as you can see, the normalized current will reduce, which means that your filament relaxation happened. And with that, we can extract the activation energy. So compare the high K and low K and to detect where the gap is. So basically using the activation energy as an indicator. And the key takeaway is that you have a high K, low K staking, you have a single layer, and I'm able to extract the activation energy. I'm using that as an indicator. And I know the sweet spot is happening when your set compliance current is at 1 milliampere. So that has a steeper slope of that self-rectifying behavior. And we found out that activation energy, which is much more higher in hafnium oxide, and which means that the relaxation rate is low in hafnium oxide, which is the filament in hafnium oxide is more robust. And the filament in silicon oxide is more easy to relaxation. So this telling us that, hey, when you want to reach to the steep slope for your self-rectifying behavior, then you need to integrate one low K layer. And I also going back to my textbook, and thank you for all my professors teaching me my solid state electronics and semiconductor physics. So I go back to I think it's chapter 6, 200 something page. And then there's an oxide transport mechanisms. There's a lot of different transport mechanisms. How does that happen in oxide? And I rule out ohmic Schottky barrier, SCLC, and what else? SCLC power low, and 2 more, I forget right now, but it's narrowed down to the Prof. And it's giving us that if you have a low K layer you reduce the K value, dielectric constant, which is related to your permittivity. You might learn in physics, and you can bring your nonlinearity increase. So which will giving you steeper slope. So this is based on the experimental data and also your the derivation for that. I will save that a little bit. Okay. Now, different materials. Is that only happen for silicon oxide? Silicon oxide already have a very low dielectric constant, which is 3.9. And it bothers me a little bit back to those days when I cannot find much more lower dielectric constant material. And I found graphite oxide. So graphite oxide, the dielectric constant is in the range of 2 to 8. And then it's showing me the same curve right here. So this is hafnium oxide state with the graphite oxide. And you do see that self-versifying behavior. So this is a magic to me. When I measure it, when I fabricate it and measure it, I found, wow, this is in a different material system and still can be happened and implement. So it supported the theory and hypothesis that I just bringing you two more slides before. So this is the key takeaway, and I will possibly skip this one. This is just area effect and thickness effect, and I want to show you analog behavior. So like I mentioned, the RN device is based on resistive random access, the filament, right? So it's formed by a lot of atoms piping up. And if you are able to remove one atom by one atom, actually you can create a lot of state. So multi-state is very important in analog because if you want to realize neuromorphic computing in your brain, then it needs a lot of states. So the key takeaway is there's a lot of different states you can realize in DC and also in AC pulse measurement. You see that there's a small little difference in your voltage, then you can change the different state. So key takeaway, if you can realize multi-state in your non-volatile memory, then you are getting closer to neuromorphic computing. And I'm gonna show you how does that realize in the neuromorphic computing, okay? I might need to skip this one. This is solving the variability, but let me get real quick on this one. So there's a lot of tail bits, and there's related to filament, and there's some post-treatment using the measurement techniques, which can saving that nonlinearity from 0 to 80. So if I started my bad cell, which is tail bit, and I do some treatment, and it will bring it back to the high steep slope. So this is just key takeaway that we can solve that variability. And so key takeaway is we don't need to give up any cell. Once you fabricate it, there's some variability. That's okay. We can do some post-treatment to bring that steep slope back. Okay. And benchmark for bilayer selectless RF. So compared to others' work, the highlighted one is my work. So as you can see, we have a different kind of bilayer staking structures, and the nonlinearity is good. Nonlinearity is the steepest slope, and also your power switching energy is reduced, and also your memory window is still keep there, it's still good. So 0 to 1, 0 to 1, there's not no interference might be happened in that in those devices. Okay. Now we talk about analog, we talk about multi-state. How does that realize the neuromorphic computing? So I go to the open source MIS data set, and there's a lot of human handwriting 0 to 9, and there's a lot of pictures. Some of you know about the MIS data set already? Maybe. So there's a open source, everyone can access that, and there's a 0 and 1 handwriting. And my task for myself is, can you tell me this one, who is writing this 0 to 9? And this is what I challenging to my device. So the device is that, okay, it can conduct with a different conductance and with a pulse number control. And this is the number of times I try to train my devices. This is the accuracy. So let's say myself, I write 0 to 9, and it has a data set, and they're gonna match together. Okay, now if that's match my own writing, then accuracy will become 100. So this is how backward propagation neuromorphic computing has been worked. So as you can see, this is the graphite oxide sample, and the accuracy can go up to 90. It's not good. It's not very good. It's like people are doing 99.95 or something, but I think it's good enough for hardware to demonstrate this data. And I'm moving forward to think about, okay, now LTP and LTD slope, how the slope can be, and can you bring the accuracy? So there's a SWIP window. This is done by my undergrad researcher, and he did some simulations on this one. So as you can see, there are some accuracy regions for your slope control as your pulse number. So this is very close to the hardware neuromorphic computing demonstration. And I think I can speak 2 more minutes about my ongoing topic, and I will leave some time to questions. So some ongoing project. So this is the ongoing project that I collaborate with Dr. Gibbs and his students. And there's we are thinking about different kind of microstructures, materials for memory technology, which might be reducing the power and which might be acting like a selector. And we keep it open-minded. We don't know what's going to happen. So the key takeaway is that we're building up this gold MIM structure, and this is helical structures growing here in NAU. And then this is all the microstructures. And I'm going to show you IV curve. So the primary data is it can be acting as a foaming-free volatile switching behavior if you're using tungsten oxide. If you're using hafnium oxide, then there will be a selectless RN devices. And it's integrated with the low K layer, as you can see right here. So basically, this is a very preliminary result, and we have a paper published on the ACS Applied Engineering material recently. So we are still trying to understand the physical modeling beyond that through the simulation or the testing measurements. So this was some of my students are doing right now. And this is the other collaboration project, which is a tungsten oxide thin film and tungsten oxide helix structures. As you can see, there we tested a different kind of memory window, and the key takeaway, if you are using helical, then your power actually reduced. So this is reset power, this is set power, and the blue one is the helical structure. So as you can see, the blue one has a lower power and switching energy than the red one. And we are still working on the papers right now. It's unpublished. And I'm very excited about this because this is quite repeatable in the box plot. Okay. Right. And one last one is the one-time programmable memory. So in every computer, you have a fuse memory. When you're turning on your computer, you're going to be reading something, huge current going through, and that's a fuse. And fuse is one-time programmable memory. That's not reversible memory. Okay, so we are trying to create some memory cells which can do self-resupplying, but also when the customer want to finalize state, they can bring it to a deep high resistance state. So as you can see, this is huge vault, as you can see in the memory cell, and this will be the finalized state, which can save all of your informations, and others cannot open your laptop. So this is kind of like application. And this is the other one we collaborate with Intel for the ruthenium oxide-based and ruthenium back-end of line compatible project. And we are still working on that. One last one is a radiation effect. So like I mentioned, NASA and International Space Station, they are interested to see, can we fabricate microelectronics chips out of Earth? And that's the reason why I think about this. If you every time you need to fabricate the chips on Earth and bring it back to outer space, there will be a lot of travel cost, right? If we can fabricate microelectronics chips, a simple functional one, it doesn't need to be a very advanced technology like 2 nanometer, but that will be a good sufficient. So what my task in part of the team is that I'm trying to think about what does that, after the RN devices has been fabricated, how does the radiation, how does the heavy ion, how does all the gamma ray, alpha ray affecting the resistance state? right? And this is the preliminary result by one of my undergrad students, Alex, and he's working on ruthenium-based and ruthenium oxide-based RN devices. So both the high resistance state current and low resistance state current increase. So well, high resistance state current reduced, low resistance state current increase. So memory window increased, and we are thinking about its vacancy increase in your filament structure. Okay, so let me conclude my talk. Thank you for listening. So selectorless RN with this bilayer dielectric state is presented as a self-rectifying behavior. Think about that. We want to get rid of that transistor integrated right next to memory, and we can reducing the sneak path current. And nonlinearity is beneficial for sneak path current reducing in crossbar array. Multi-level cell application by pulse modulation are demonstrated for high storage class memory. And if you have 10 bits, which is not very good bits, you can do the pulse treatment and bring it back with the high selectivity. Synaptic behaviors of the self-selective RN can realize those synaptic behaviors and also neuromorphic computing using a mixed data set for 90% accuracy. And we compare the nonlinearity power memory window for the crossbar array using this bilayer selectorless RN. And there's still a lot of memory related topics going on right now at the NAU. So please let me thank you, my collaborators and sponsors right here in this slide. And also there's international collaborators as well. Okay, so I think this is my talk, and thank you so much for listening.
Thank you very much. Daphne, some questions? Please.
So with the nanophysics, do you know what the mechanism is like physically about that structure that's allowing the power to be lower? Like what's going on that structure has lower?
Very good question. Very good question. So I think I might discuss with John a little bit, but the pre-cumulative observation we are currently I'm thinking about, and the hypothesis is because this concentrated electrical field. So if you can, so think about that. Usually the filament is going this way, right? But if there is a accelerating process, like much more longer structures of that, there has much more concentrated electrical field, which might help the filament to grow, and that will be reducing this weakness. But we still need more results to support that. Okay, I hope that answers your question.
Other question? Yes, please.
Yes.
So, like your system, you get some sources of interference happening. I was wondering, what are some of the major sources? What are they?
You mean in the crossbar? Yeah. The key components for it. So basically, let me see. So, like I mentioned, so this is all your neighboring cell. And if you want to read or write this selected cell, there's a lot of paths still going through. So this is V, this is grounded. So there's a voltage drop. Once you have a voltage drop, you have a current. So that's an interference. And if you're going to the circuit level, there will be much more interference, but I'm talking about bus level. So yeah, pretty much.
Okay. Any other question?
You mentioned earlier the employment component, and I'm asking whether or not you have students that are performing the measurements to get those butterfly curves, or do you get those somewhere else?
Yeah, I'm remembering it.
And how do you?
That's a great question. Yeah. So we're using the we're using the Prof station. I should show the slide. Let me check. Oh, I do have slide. That's right. So, well, I should not put the monitor on top of it. Sorry about that. That's but I mean, we proved that. This is just beginning of my lab. So this is Prof and a microscope. So I don't know if you guys know, but one device is much less than your hair. Your hair is like 80 micrometer, but one device is like a 15 micrometer, something like that. And we can go even smaller to the nanometer. But we use this probing station with this analyzer, semiconductor analyzer, so we can get a butterfly curve. And also the pulse measurement.
So some kind of scanning probe.
Not quite. It's like electrical correlation probe. So there's should be some conductive probe. Probing on is like Harley probe and probing on your device. So yeah, there's a conductive pad. Oh, it's a good picture actually. There's a conducting pad right here. So you see this probe. This probe tips is 12 micrometer. So which can probing on your devices. Okay. Yeah.
Another question? Rob?
A very primitive question. The filaments, what do we know about, what are they made of? What's the filament made of, and what do you know about the microstructure of the filaments? Are they reversibly formed? And just
I'm so glad you're asking this. This is so important questions. So filament, is within the oxide, silicon oxide, hafnium oxide, metal oxide. So we do have some metals. And with the breakdown, it will piping up the oxide. So it will creating the oxide vacancy. So which will lift the metal rich site on that. So which will be conductive. That's one kind. And the other kind is if you're using diffusive electrode, that will be the metal will be diffused into the film. So there's two kinds of resistive.
and in that second case with the diffusive electrode, is that what you said? Diffusive?
Diffusive metal like
What?
gold, no, like silver and copper. Yeah. And your second question, is that reversible? Yes. So you can make it conductive or you can rupture it. So right, 0 and 1, 0 and 1. So that's how the principle for the RF devices.
And then I have trouble with, you started with this nice image of Professor Chua in Berkeley, and you showed a pinch. If it's a pinch, it's a membranosphere. Some nice quotation like that. Or if it's a membranosphere, there must be a pinch. Now, is the pinch the loop, the double loop, the infinity symbol? When you switch to showing all your IV characteristics,
It
it's
doesn't
on a
look.
semi-log plot, and everything is positive, right? Because it's DIV. Is it the same?
Yes, thank you for asking that. So we do absolutely value for current. So if you apply negative voltage, you should get the negative current. But for the reading like convenience or
Right.
like people are used to read it like that, so it will flip up on the negative side. But you are right. Originally rolling that would be like positive and negative.
Yeah. And then in the one with the historical slide with Chua and the infinity symbol, the butterfly, I guess is what Jorge called it. Maybe not the same thing, but that's just a single IV measurement, right? This has this huge hysteresis.
It is one cycle.
It's one cycle.
Yes.
And then when you switch to showing all your device characteristics, your memristor characteristics, you would have multiple, do you call it stop potential?
Oh,
With
you
the
mean
nonlinear.
the
It was slide 31.
31. Thank you for making it easier.
But it could be Dr. Gibbs device. Any of the ones that,
Is this one?
yeah,
Oh,
any one of those.
how about this one? Is that this?
That was beautiful.
So can I have a version there?
Well, maybe this one's too simple, but you had some where it looked like when you do the sweep of the IV measurement, you stopped at different potentials and you listed for different stop potentials some characteristics like
Maybe this one.
Yeah,
Right.
that's
So this is stopping point. Like, yeah, I control the stopping voltage and you can control different states. Yeah, so like, this is basically how you control the filament shape. So the more you reset it, the gap is becoming huge and huge. So that will be more high resistance state. So if you reset more, then there will be more high resistance state. And if you just do a little bit small reset, then the switching gap is so close to each other. So, yep,
But these, every one of these colors is a pinch.
yes,
They're all the
It is.
same as we saw. Okay.
yes, and
It's just a different way of presenting it with the semi-model
yes, yes,
and negative. and positive.
yes,
Thank you.
yes, thank you.
Okay, we have time for the last question. Please, Angel.
So you mentioned that they have like neuron imaging characteristics, these devices,
Yes.
and AI, so do you think that makes them more better optimized for AI algorithms?
That's a good question. Well, you can control either from your algorithm side or device side. So from two different perspectives.
This is a hardware-based AI.
Yeah, this is power-based AI. Yeah, correct.
Well, thank you very much for this very. Thank you very much. Very, very much.
So much.
Let me, yes, but let me tell you, we are working.